Hello everyone, my name is TANG Wei and I'm very delighted to give an introduction of our group project. The topic is about Deepfake, which is a deep learning application that has exploded in popularity. Our presentation will be divided into 3 parts, and the next 2 sections will be explained by my partners to help you learn more about Deepfake. Before I go through the definition of Deepfake, let me show you a piece of video. This video has been clicked over 10 million times on Bilibili, which is a popular website in mainland of China. So this guy is a famous game producer in China, and this video is exactly what I mentioned before, a deepfake. It's not that the man actually sings the song, it's just that the original person was replaced by his face. With a neural network, a deepfake can replace human's face without modifying the original facial expression. In our project, we applied this kind of technologies and generated 4 persons deepfake. The datasets we use are from Baidu AI Studio and Renxiang. The main platform we use is TensorFlow 2. At the same time, we utilized a lot of deep learning libraries to support our model training, such as OpenCV and the NVIDIA CUDA. Next, let my partner HUANG explain the details of our model for you.
Hello everyone, I will introduce our models and algorithms in our models. First, we need people sensing the input images. This step is aimed to enhance the performance of models. Making minor alterations can enlarge the datasets, transforming 256 by 256 images into 64 by 64 images so that the neural network can focus on human face attributes. Regarding the generalization abilities, the remapping algorithm is applied. Optimizing the batch size will increase memory utilization and making the models converge more efficiently. Our model consists of 3 different parts: encoder, decoder A, and decoder B. Similar to the UNet architectures, encoder part is used to downsampling the input images, and both of decoder A and decoder B is used to upsampling the images. During the backward propagations, encoder can capture the face features, decoder A and B can reconstruct the spatial features. For example, we want to exchange Trump's and Catch's face. This graph shows the path of forward propagations. If we want to replace Trump's face by Catch's face, we'll use 2 Trump's face images to do encoder-decoder B operations, and we can see the Trump's face was replaced by Catch's face, and the same for Catch's face. Here is the detailed architecture of our training models. From the graphic, we can see the encoder part is consisted of 4 convolution layers, 2 flow connection layers, and a upscale layer. And the decoder part is consisted of 3 upscale layers and a convolution layer. Upsampling layers contains a convolution layers and a subpixel convolution layers. In upscale layers, we use subpixel convolution, or called pixel software, which is an ingenious upsampling method. Compared with the previous common upsampling algorithms, this approach has a significant improvement in both speed and quality. Here, this graphic shows how subpixel convolutions improve input images resolution.
Thanks to my teammates. Now let me show you what performance of the model looks like. I'm going to start with an amazing advanced technology, GPU, higher computing speed. The future of computing has arrived. NVIDIA CUDA Deep Neural Network Library is a GPU-accelerated library of primitives for deep neural networks. Faster and flexible, is the two important features. cuDNN convolution routines aims for a performance is competitive with the fastest GEMM. Based implementations of such routines will using significantly less memory. cuDNN features include customizable data layouts, supporting flexible dimension ordering, threading, and subroutines for the 4D tensors used as input and outputs to all of these routines. Its flexibility allows easy integration into any neural network implementation. Here is a comparison. Our speed has increased more than 6 times. That's amazing! The second part is the result. Thanks to the new technology of GPU, we can train 9,000 times and more. And you can see the results are very interesting. The phase change between tramp and cage was very successful, as if it were real. But the results of Zhou and Fan Bingbing were not very satisfactory. And the spatial angles and expressions, the performance of the model is very poor. There are always limitations in any experiments. In future research, we can optimize the algorithm and the model structure to improve training efficiency. Also, GPU acceleration is used. We can still further enhance the performance of the computer and extend the training time. Finally, we need to apply more computer graphics knowledge such as Poisson blending and edge blending. That's all for our presentation. Thank you for listening. Now is the question and answer time. Feel free to ask.